All right. So in lithium, we have 3 electron here, 3 proton here. So we have 3 proton, 2 electron sit like this, and 1 electron goes here. Right? Now, the effective nuclear charge, we don't talk about this one, we talk about this one. So the outermost orbit, right? So effective nuclear charge of the lithium for the outermost electron is, if Z, we write ZEFF, so that is the effective nuclear charge felt by this electron. Yeah. So effective nuclear charge felt by this third electron in lithium is calculated as 3. So this is the number of protons minus. So some of the force of this proton is diluted by these 2 electrons. So this and this electron dilutes the force of these protons to this electron. Yeah. So we need to put these 2 electrons. So these are the diluting guys. So they diluted the force. So that is, so Z effective for the lithium is 1, right? So you may think that, okay, this electron is negative, so there are 3 protons, so 3 protons are pulling with all its strength this electron toward themselves, but that doesn't happen because these 2 electrons already block some of the charge of this one, and this electron cannot fill all 3 protons here. It just fills 1 proton. Yeah. So sometimes you can experiment with the magnet. So if you put a big block and one magnet up and one magnet down, they don't attract that much. But if there is a thin surface, they attract with a high force, right? So something like that. So effective nuclear charge for, again, this is not the exact effective, it's estimated. A little bit lower or a little bit higher than it is exactly. So our book doesn't discuss that, so I don't discuss that exact effective nuclear charge. Yeah? This is just the effective. Now, we already have lithium. Now let's talk about the beryllium, right? The fourth one. So beryllium is the fourth. We have four proton here, 4 proton, and so 4 protons, 2 electron here, so 2 electron here in outermost, right? So how much force these 2 electrons are attracted by these 4 protons? So that is, we have the 4, total charge is 4, and already that force is diluted by these 2 electrons. So 4 minus 2 is the effective nuclear charge. So by about, out of these 4 proton, maybe about 2 proton are able to attract these 2 electrons. So that's mean that. Yeah. So now let's talk about the boron. So boron is I have this is a 5, atomic number is 5. So we have 5 protons here. Now 2 electron here, 3 electrons in this orbit. We can put up to 8 electron in the second orbit, right? In the first orbit, we can only put two electron according to 2n square. In the second orbit, we can put up to 8 electrons. So so that is 5. So we have the 5 proton, but that force is 2 of the those are neutralized by this, meaning that the force is diluted by these 2 electrons. So that's the number of electrons. So that's a 3. So you see that. So in beryllium, the outermost electron experience about 2 unit force, right? But in boron, the outer electron experience 3 unit force. So it's attracted much toward itself. Yeah. Now, if you go to the carbon, carbon is number 6. So proton is 6. So I'm not writing neutron there. So 2 electron there, 1, 2, 3, 4. So now it is 6, right? This is a carbon. Carbon has a number 6, 6 electron. Now out of this 6, so 2 dilute the about 2 force, and then so for carbon it will be, this is 6. So carbon has a 6 electron, 6 protons. So ZEFF, Z effective for carbon is total charge is 6 minus this 2 electron is going to block this outermost electrons to reach that force there. So that is minus 2 is equals to 4. So carbon has 4, right? Make sense? So in carbon, outermost electron are experiencing a 4 unit kind of force. Yeah. Now this is a Z, so they call it the Z effective nuclear charge. Now you can keep going. You go to the 7. 7 is nitrogen, and then this is 7. So 2 is already there. 1, 2, 3, 4, 5. So total electron is 7. So 2 is these two are blocking the charge. So 1, 2, 3, 4, 5. So about five unit force these outer electron are experiencing from this proton, right? Same, just keep doing that and put 8 here. So 8 is oxygen. 8 is oxygen. So there is 8 proton. Then electron is also 8, right? Number of proton and number of electron are same. So 2 already there. So 1, 2, 3, 4, 5, 6. Now see that number of electron are also 8. Now if you calculate the effective nuclear charge, that is ZEFF for oxygen would be total charge, positive charge is 8 there, and these two are diluting that force by 2 units, and outermost electron experience about 6 unit nuclear charge. Yeah. So we just take the number of proton and subtract how many electrons are inside, and that is the effective nuclear charge. Now I'm going to write another one. So let's write 2, 4. So 2, 4, 6, 7, 8. So this is like that, and let's talk about this one, right? So this is one. So what is this one? So how many electrons here? 1, 2, 3, 1. This is 2. These are 8, 8 to 10. This makes 11. So look the periodic table. What is the number 11? That's a sodium, right? So number 11. So there are 11 electrons. 11 electron meaning that in periodic table you can go look there and see that's a sodium. No, it's not writing. Sodium. So this element is sodium. So if there are 11 electrons, there are 11 protons, right? So 11 proton. Number of proton and number of electron are equal, right? Now if you have to calculate the Z effective, the effective nuclear charge felt by this electron. We are not talking about the inner electron, because most of the reaction happen in the outermost orbit, not inner side. Yeah. So Z effective nuclear charge is 11 proton minus how many inside we have? So 2 here, 8 here, 8, 10. So 10. So that is 1. So effective nuclear charge felt by this electron from this one is just to be 1 unit. Yeah? Just like this. Just keep repeating that, and that's the effective nuclear charge. And with this one, we can explain a lot of things later. It's very important. Yeah? Good. That's how we calculate the effective nuclear charge. All right. So all right. So so let's see here. I have now. Now look the periodic table. So when you look the periodic table, so periodic table shape look like this. So look like this here, and maybe there are multiple columns here, and there are multiple columns here. The periodic table look like this, right? And you will see hydrogen here, and below hydrogen maybe you see the lithium, and below lithium you see the sodium. Below sodium you might see the potassium and rubidium and cesium. So something like this you see in the periodic table. Yeah. So look the periodic table and you see something like that. And in the second one you see the beryllium. I don't know, maybe magnesium. So the magnesium. You see the magnesium here, and then calcium here, and after rubidium we have a strontium here, something like this, right? Now let's talk about, so we draw like this. So this is called group. So this is called group. So if you look vertically, this is called group. All right. So this is called group 1. Group 1. This is called group 2. This is called group 3, group 4, group 5, group 6, group 7, and group 8. So this is called group. Yeah. So vertically is called the group, and the row this way is called the period. So this way, if you look this way, it is called period. Period. And if if you look this way, this is called group. Yeah. So what happens to the size of the atom if we move from hydrogen to lithium to sodium to potassium, rubidium, cesium? What happens? Would the size be bigger or size be smaller? Is lithium is bigger or sodium is bigger, or sodium is bigger or potassium is bigger? Yeah. Or potassium is bigger or rubidium is bigger? What happens? And what happens if we go from lithium to beryllium, like across the period? What happens? Will this be bigger or this be bigger? So something like this we are going to talk, and that is called the periodicity. Yeah, periodic trend, not periodicity, periodic trend, periodic trend in size. So let's talk about the size first. Periodic trend in TREND, trend in size. So when you go from here to down, so the size of the atom look like this. So hydrogen looks very small like this, and the helium looks, the lithium looks a little bigger, and then sodium looks even bigger, potassium looks bigger, and the rubidium looks even bigger, the cesium looks even bigger. So the size of the atom, when we go from top to bottom in a group, the size increases like this. Make sense? So toward up, the atoms are very small. As we go down, the atoms become big. Yeah, the size increases as we go down the group, and no matter which group, everywhere. Yeah. So whether here or here or here, just look at the periodic table. The size of the atom somewhere here is bigger than there. The size of this atom is bigger than there. Yeah. So upper part, the size are smaller, and then now this is boron, this is carbon, this is nitrogen, this is oxygen, maybe this is fluorine, neon, so something like this. So look the periodic table along the lithium, beryllium, boron, carbon, this looks like this in periodic table, right? So what happens if we go like this way? So that is like this. So if you look the group, the size of the atom becomes bigger and bigger, right? Just like this, yeah? Now if you go from this way to this way, the first one looks big, like this. The another one looks a little bit smaller than this. Then this one, even smaller. Then this one, even smaller. This one, even smaller. This one, even smaller. Tiny, small, like this, yeah? Make sense? So just imagine the marble, and you are arranging the bigger to smaller marble like that. Yeah. So the size of the lithium is large, beryllium is small, boron is even small, carbon is even small, nitrogen size is even small, fluorine has a very small size, neon is the most smallest size of the atom in that period. So this is across the period. I'm just talking about only one. Yeah. I'm not comparing the material here to here. Yeah. I'm just talking in only along one period. Make sense? Good. So, and also I am just talking about the only one group. So either with this group, or this group, or this group, or this group, or I am talking about this period, or this period. I am just talking in only one period. So this is what happens. So why this happens? Now we need to bring that effective nuclear charge to explain this phenomena. Yeah. So let's talk down. So first of all, let's talk about the lithium. So we need to write the lithium electronic configuration first. So lithium has number 3, right? Lithium is in number 3. So lithium is in number 3. So how many proton it has? It has 3 proton and 3 electron, right? So 3 proton, 3 electron. Now draw the picture. Draw the figure of that one. So I don't know why it's not. This is not writing well. So it looks like this. So this is a lithium. So we have a proton here. So how many proton we have? 3 proton. We have 3 proton here. 3 proton. Lithium is number 3, so it has 3 proton, right? You can look the periodic table and you can easily see that one. And then so it has also 3 electron, right? Yes, 3 proton and 3 electrons. So I'm going to write 2 electron in the first orbit. So I write the 2 electron in the first orbit, and I write 1 electron in the outermost orbit. Now I calculate the effective nuclear charge here. So what is the effective nuclear charge here? So 3 minus 2 is equals to 1, right? So this electron just being attracted by 1 proton, right? The force of the 2 proton here is already neutralized by this inner electron. So this electron can only feel about +1 charge. So this electron is pulled toward itself by about one unit force, right? So this is an effective nuclear charge. Now let's talk about the beryllium here. So beryllium has a number. Beryllium is a number of 4. So it has a 4 proton and 4 electrons. So I'm going to draw this structure again. So this is a 4 proton. I'm writing a 4 proton here. So inside I have 2 electron like this, right? Now outside I have another orbit. Now I have 2 electrons here, right? in the first orbit we cannot put more than 2 electrons. In the second we can put 8 according to that 2n square root, right? Now let's calculate the effective nuclear charge. I have the 4 proton, 4 plus charge here. Now that out of 4, some is neutralized by this 2. So I minus 2. So I get 2 plus 2. Kind of this is plus 2. This is I write the plus 1, right? So you see these 2 electrons are attracted by plus 2 force, right? It was just attracted by 1 force. So it was it really didn't move toward the nucleus. But since these 2 electrons are attracted by the more force here, so what happens is that this electron orbit becomes contracted. So it just become like, okay, so they experience too much force, so these electrons go toward inside. You see that? So this was a bigger and this becomes smaller. Yeah? So this is the second orbit becomes now small. So since we have a 2 electrons, so this was big, this is small. Why? Because these 2 electrons experience larger amount of the force from here, so the orbit contracted and becomes small. Yeah? Just like the squeezing. Yeah? So you have a ball and if you squeeze it with a great force, it becomes small, right? So these protons try to squeeze that out of orbit just by pulling those 2 electrons toward them. So this is even smaller. Now, if you go further from, let's say, beryllium to boron, so let's talk about the boron. So boron has a 5. So they have 5 protons here. Now, in the first orbit, they have 2 electrons, and in the second orbit, they have I think I need to be a little bit. So in the second, they have 1, 2, 3, like this, right? Now, if you calculate the effective nuclear charge, 5 are positive here, and then these 2 electrons inside are diluting some force, and that is equals to 3. So this electron experience plus 3 charge, and the size become even smaller. Make sense? Easy? So there was only 1 positive charge here, the effective nuclear charge here. So this was not being attracted that much. So that just diffuses and it becomes like a big one, right? And but here, this outermost electron experience plus 2 charge from here. So that attracted more toward it, and then the size of this becomes smaller. And further you go there, the effective nuclear charge experienced by this outermost electron is 3. So all electrons are experiencing even more pull toward the nucleus, and this becomes smaller. The size decreases, and they just keep going like this, and then as you move further, the effective nuclear charge becomes more and more for those outermost electron, and the size becomes smaller and smaller and smaller. So this is the smallest one. This is a little bigger. 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 This is the biggest one, right? Make sense? Good. All right. So now we could explain what happens in the period. If you go in the left to right in a period, so the left are the biggest and the right are the smallest. Yeah. So in the next homework, you will see something like this. So I will put the name of the atoms, like I give you, okay, boron, carbon, nitrogen, oxygen, these elements, and I give us arrange them according to the size. Yeah. So which one is bigger, which one is smaller? Easy. Now let's talk about the group. So once you understand this concept, we just use in another thing. So let's talk about that one. So I start with the lithium. So let's take lithium and let's take sodium. I put this lithium and sodium in the PowerPoint slide. So let's draw this one. So lithium is 3, right? Hydrogen, helium, lithium. Lithium comes in number 3, right? And then so it has 3 proton and 3 electrons. Sodium comes in 11. So it has 11 proton and 11 electron, right? So now we need to do 2 things here. One, we need to look the size, and we need to look the effective nuclear charge, and we see which one will win, whether the size will win or the nuclear charge will win. So I'm going to draw this one. So this is a lithium. So I put the proton number is 3. Proton number is 3 because number of proton in 3, number of electron is 3 in the lithium. Yeah. Look at the periodic table and you easily know. So now I draw the first orbit here. So I put in the first orbit we cannot put more than 2 electrons. So this is the maximum number of electrons we can put according to n square, right? N is equals to 1, n square is equals to 2n square. So 2 multiply 1 is 2. Now I have a third electron here, and I'm going to put here one more electron here, right? So lithium looks like this, right? And now I'm going to draw this. Now let's calculate the effective nuclear charge here. So ZeFF would be, so I have a 3 positive, so 2 inner electron dilating that force, so 3 minus 2 is equals to 1, right? So effective nuclear charge experienced by this outermost electron in lithium is 1, right? Good. Now let's talk about the effective nuclear charge in sodium. So I'm going to draw that one again. So the number of protons is equals to 11, and then this is the first orbit. Okay, I might have done bigger, so don't get confused. So this is the first orbit. So to here. Now I have another orbit here. Another orbit. This is the second orbit. According to 2n square rule, 2 n is equals to 2. This is n is equal to 1. So I put 2 electrons. N square is, this is n equals to 2. So n square would be 4. 4 multiplied by 2 is 8. So in this one, I can put 8 electrons, right? In the second orbit, I can put 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So I put already 2 here. Now I put here 8. So 8 and 2 becomes 10, right? Now I still have one more electron, right? So that electron I cannot put here. We cannot put more than 8 electron in second orbit. Now I'm going to put another orbit here and put that electron 1, right? So something like this. Now I'm going to calculate the effective nuclear charge, ZeFF here. Z effective nuclear charge is how much here? So I have 11 charge here, 11 positive charge. So this force is diluted by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons of the outermost orbit, right? Now this is also 1. So effective nuclear charge experienced by this electron is also 1, right? And this is also 1, right? So that only effective nuclear charge cannot explain this phenomena. So what we should say is that in the although the same effective nuclear charge experienced by this electron here, but this electron is being added to which orbit? Third orbit. But here there is no third orbit, one is second orbit, right? So size of the third orbit is too big compared to even if there was a more this time there is I can see the effective nuclear charge is same, but even if there was a bigger effective nuclear charge here, the size of this third orbit is too big, right? So when the electron is added in the further from the nucleus, that's going to give you a large size of the atom. Yeah. So there are only 2. We are talking only second orbit radius here, second orbit radius here, from here to here, only second orbit radius here. But here we are talking about the third orbit radius here. So third orbit radius is always higher compared to there is a more nuclear charge. It cannot affect that. Yeah. So kind of something is too far already, and even if you put the nuclear charge here, that cannot pull something from all the way back. Yeah. So that's too big. So how we explain this one? So this one is in sodium, the last electron is in third orbit. Third orbit. See that in the sodium, the last electron is in third orbit. So third orbit has a too big size. So third orbit is bigger, much bigger than second orbit. So this is definitely bigger in size. Now if you go down, so lithium, sodium, after that what comes? Potassium comes, right? If you look the potassium, the number of the potassium is I don't know, 19. So it looks like a 19, right? So 2 goes there, 8 goes there, 10, and then goes here, 8 goes here, 18, and the last electron will be added here in the next orbit. So this becomes even bigger because the electron is being added all the way back, right? The nucleus is here, So the electron shifts all the way back. So the size is too big, the radius is too big. Yeah? Make sense? Easy. So if you go from left to right, the electron is added in the same orbit, and effective nuclear charge is more. So the electrons are attracted more and more, and the size decreases. But as we go down from top to bottom, in each step, although there is a increasing nuclear charge or the proton charge, in each step the electron is added in the extra another orbit. Yeah, so that orbit has a bigger size, so that makes the size of the atom bigger. Make sense? Good. Alrighty, so this is very important concept. With this concept, we can talk about the electron affinity and ionization potential. Yeah. So good. Right. So what I have here, I just want to. So I already wrote that thing in the slide number 4. You can read in home. In slide number 5, they are talking a little bit about how to define the atomic radius, the radius of the atom. Yeah. So just like the circle. So if you have a circle, so this is the center to circumference is the radius, right? Now think about the golf ball. So this is a golf ball, like this is a circle, this is a golf ball, it's a sphere, and there is a center somewhere, and from center to outermost space is called the radius of that golf ball, right? Now, same thing. So talk about like this. So let's say we have a chlorine molecule. So chlorine has, let's say we have a Cl2 molecule, and since Cl2 is 2 atoms, so 2 atoms has the same size, right? Because this is chlorine and chlorine, right? So let's say this is a chlorine, one chlorine, and in real life, these chlorine atoms are living like this. So same size like this. Yeah? So this is one chlorine, this is another chlorine. So maybe you see here this is different size than different size, but it's not. Just I couldn't draw the exact same size. Yeah. So this is a chlorine, and this is also chlorine. So we have a 2 atoms sitting together and giving the chlorine molecule. And so from the center of this one, to the center of this one, so we measure the distance. So this distance is measured. Yeah. So there is a way to do, but we don't discuss those things here. So this distance is from the center of the one atom to center of the one another atom in chlorine molecule. The distance is 198 picometer. 198 picometer. So one picometer is equals to 10 to the power minus 12 meter. Yeah, 1 picometer is equal to 10 to the power minus 12 meter. So 1 nanometer is equals to 10 to the power minus 9, right? But we are talking a picometer here, not nanometer. So this is a 198 picometer. So then divide by 2. So they are talking from here to here, but the radius of the atomic radius or radius of atom is just this much. So this total gives you the atomic diameter. Now atomic radius is given by 198 divided by 2. So from here to here. So that's the atomic radius, right? And so that is 98 or 99. I don't know how much comes. So that is 99 picometer. Yeah. So first of all, you need to have the molecule, and then measure the distance between the center of these two atoms in that molecule, and then you divide by 2, and so that you get that radius and the radius. That's the atomic radius. It's the size of the atom. Yeah. So sometimes people may give the radius of the atom or the diameter of the atom. So most of the time we talk about the radius of the atom. Yeah. That's it. Now, suppose this is I just talk about the chlorine, because I have same atom, right? Chlorine, or hydrogen, or lithium. I just talk about the same molecule containing the same atom. Now, same kind of atom. Now, if you have a different kind of atom making a molecule, so this is a hydrogen, this is a chlorine. So this is a hydrochloric acid, right? Hydrochloric acid molecule, right? Now, how to define the atomic radius here? So So this is the center of that one. This is the center of that one. Now you are going to draw this one. You see, now you already know the atomic radius of chlorine from here to here. That was 99, right? So that was 99. Now what is the atomic radius of the hydrogen? You can easily calculate. So atomic radius of hydrogen, atomic radius of another guy, or let's say atomic radius of hydrogen. Atomic R is the radius of hydrogen. So that is, so first of all you need to measure from here to here and subtract this one. So that is what they are writing the carbon. Let's say carbon and chlorine. So atomic radius of carbon first. Radius of carbon is total. They did the number from here to here in that molecule is 176, and then from here to here we already know that is 99. So so the atomic radius of carbon would be minus the 99. That's the subtract that one, and 176 minus 99 will be 77 picometer. Yeah. So measure from here to here. And you already know the radius of one of this, and just subtract from the total to that one, and then you get the radius of the remainder one. Yeah. So once you know, you just think about just two marbles, one bigger, one smaller, and just you can just it's just exactly the same, right? All right. So that's the atomic radius of carbon. That's how they calculate. In slide number 6, what I already showed you this sphere. So lithium, sodium, then potassium, then rubidium. So they are saying this one, yeah, exactly same thing. So the size of the lithium they are giving 152 picometer. Size of the sodium they are giving 186. The size of the potassium is 227. Size of the rubidium is 248 picometer, and then the big guy, this name is cesium. This is 265 picometer. So the radius of the atom is increasing from top to bottom, right? So so you look another one. So beryllium is 113, magnesium is 160, calcium is 197. Keep going, and all the way down there is a barium, and that is a 217. So its size is increasing. Yeah. It's pretty straightforward, right? Good. Now you can just go from left to right and see. So let's look left to right. So let's look the lithium. So they have the lithium here, and they are writing 152. So this is lithium. So this is 152. Then they have the beryllium here. They are writing 113. Then boron. They have the boron here. That's 83. Then they have carbon. That's 77. And then for the nitrogen, they have nitrogen. The size. So size of that nitrogen is 71. That's all picometer. Then we have oxygen. Sorry. So nitrogen. Then we have oxygen. Oxygen have a value of 66, even smaller. And then we have what is there? That's the in the 7A. You will see all this. There is a 7-1. Sometimes this number can fluctuate a little bit different than expected. We will talk about that. Yeah, that is called the anomaly. So in this one, they are 66. You would expect the last one being like this, and you would expect the maybe 61, or maybe you would expect a 50, right? Yeah, because this is smaller. But this the last one. They are writing 71, slightly bigger than this one. So sometimes it doesn't follow exact trend what we expect. Yeah, sometimes there is a little bit anomaly, and why it comes, we need to talk later. Yeah, make sense? So don't get confused too much here. But you just look the measure thing. So 152, 113, 83, 77, 71, 766. Up to here we are good. So there is a tiny bit variation there. Why it comes? So they try to explain that with certain reasoning. Yeah? Good. So the size decreases like that. Good. Now the same thing in the look another row and another row, and everywhere is same. Now in slide number 7, they are talking exactly the same thing. Size goes up. So if you come from this way to this way, size becomes bigger. If you go from here to here, size goes bigger. But if you go from this way, size becomes smaller, right? So just don't get confused. Sometimes the book side, oh, I go from the left to, right to left. What happened to the size? It's the same thing. So if you think, if we already know that going from this way is decreasing, so if that one way is decreasing, going from this way to this way is increasing, right? The same thing. So don't get confused with how the book write. Yeah. So left to right is definitely decreasing. Meaning if you go to right to left, then the size becomes bigger, right? So they're saying the same thing. So here is a problem I took from the book. So let's practice this one here. So in the slide number 8, we have the potassium, rubidium, the first one I'm working here, sodium and cesium. Which one is the biggest size among this element? That is the question. Now you go to the periodic table and look the where are those elements? So first you have lithium, then after lithium you have a sodium. You have a sodium there first, and then after sodium you have potassium. Just look the periodic table. Yeah, I'm looking the periodic table. Then sodium, potassium. After potassium you see rubidium, and after that comes the cesium. Right? Look the periodic table. Yeah. So in periodic table the elements are arranged like this. So which has the biggest size? So this is the biggest size, right? As we go from top to bottom, which has the size increases, right? It's pretty straightforward. It's not like the quantum electron speed. It's not like that. It's a very straightforward thing. Yeah. So this is the biggest size. So I might put in quiz which has the smallest size. This one, right? Or I might put something like that. Okay, I have this one. Na, potassium, rubidium, and then CS. I might like something like this. Something like, is it bigger or this is bigger? This is the biggest. This is right, right? The order is right, right? So sodium is smaller than potassium, potassium is smaller than rubidium, rubidium is smaller than cesium, cesium is the biggest one, right? So I might put like something like this and just find which one is right, right? So this basically is saying that sodium is smaller than potassium, right? So you can write it this way. So if I try to give you wrong answer, so it is saying sodium is bigger than potassium. Is sodium is bigger than potassium? No, potassium is bigger than sodium, right? This guy is bigger than this one, right? Make sense? So don't get confused. If sometimes you will get something like smaller than or greater than this sign, so don't get confused there. Same thing, yeah? It's just like 2 is it right? 2 is smaller than 1, is it right? No, right? 2 cannot be smaller than 1. So 1 is it right? No, 1 cannot be bigger than 2, right? So it's just like 1 is smaller than 2. This is right, right? Okay, good. Now, another one, which has the biggest size among aluminum, chlorine, magnesium, and phosphorus. So I think they are asking, look the trend. So which way they are talking here? Aluminum. So they are talking along the, across the period here. Yeah. Now let's look the period here. So in the period, where is the aluminum? Is the second period. What is the first element in the second period? That's the magnesium. So the magnesium is the first. Look the second period. Magnesium is first, and then aluminum comes after magnesium, and then after aluminum comes the what comes there? Then aluminum, magnesium, aluminum, and then comes the sulfur, and then only comes the chlorine, right? Look at second period, right? So you need to look the periodic table. So don't get confused there. Just look the periodic table. In the first, they have the magnesium. Among these elements, first is magnesium, second is aluminum, third is sulfur, and the last one is chlorine, right? Now apply the periodic table. So going from this way to this way, the size decrease or increase? Decrease, right? So I already told you. So this is too big. This is a smaller. This is even smaller. This is tiny, like this. When we go from the left to right, the size of the atom decreases. So which one is the biggest one? This guy is the biggest one, right? Magnesium is the biggest one. And if I ask you which one is the smallest one, the chlorine is the smallest one. So they could put further argon. So argon. So this would be even smaller than chlorine, right? Should not be confusing. It's pretty straightforward, right? So just arrange the element in that period and see. So the magnesium is the biggest element here. Now let's look something like this. Can we do something like this? So NPO. So I want to compare the size of these three elements. So look the periodic table. Can we compare the size, the nitrogen, phosphorus, and oxygen here? Look the periodic table, and N and P are in the same group. So big. This is small, right? Make sense? This is small. This is big. Now this is oxygen. This is oxygen. This is not the circle. This is oxygen. Yeah, I'm looking N, P, and O. Now my oxygen is here. Oxygen is here. So oxygen is here. So is the oxygen? Let's write oxygen here. So is this big or this big? Going from this to this is bigger, or which is bigger? This is bigger or this is bigger? Definitely this is bigger, right? We are moving this way, is the size decreasing, right? Make sense? So going from here to here is small size. Going from here to here is a bigger size, right? So which is the biggest size here? This guy is the biggest size, right? Compared to this is the biggest size. So phosphorus is a big guy because it's in the another level down there. And then now let's compare this and this. This is bigger or this is bigger? This is to the left side, this is to the right side. So this is definitely smaller, right? So this one is very small. And then nitrogen is somewhere in between. So phosphorus, nitrogen, and oxygen. Make sense? Maybe this is a little bit confused because I am comparing two groups. This is one group and this is in another group. But you can easily compare this one because this is in the upper top. So top is always smaller. The bottom is always bigger according to the rule, right? The nuclear charge, whatever we talked earlier. And then if you go from left to right, the size becomes smaller, right? Now which is the biggest? This is the biggest because it is toward the down. And then this is the smallest because this is toward the right? And this is somewhere in between. Make sense? So there is a question these authors were putting there. So I will put that question in next quiz. Now we talk about the ionization energy. So the ionization energy. So what is ionization energy? Ionization energy, or sometimes they call the ionization potential. Ionization potential, same thing. Potential is energy, yeah? Potential, we call IE or IP. It's the same thing. So we already know about the hydrogen atom. So hydrogen atom has one electron here, and we have one proton here, right? So there are a lot of spaces here, and if you hit it, this electron is going to jump here, right? Further hit it, this electron is going to jump here. Give more hit, it is going to jump here. Give even more hit, it's going to go here. Give even more hit, then it's going to leave and going away. This is fly out. So that amount of hit you give is called the ionization potential. So how much hit? The amount of hit, so that the outermost electron just fly away from the atom, no more with the atom anymore, right? Just we studied in the photoelectric effect last time, right? So in the photoelectric effect, I was talking like this metal surface, and you give some photon, there is an electron there, and just eject that electron out. But in photoelectric effect, the atom should not be in the gaseous state, but in the ionization potential, this atom must be in the gaseous state. That's the difference, yeah? So imagine there is a atom, and that is in the gaseous state, right? Now you give the energy, that much energy, so that electron just, the valence electron, the outermost electron just fly away, leaving behind the atom, right? And that is called the ionization energy. All right, so that's the ionization energy. So two things, very important two things here. One thing, atom must be in gas phase. gas phase, and in number 2, give energy to that atom, give enough energy, just enough energy, not big, not larger energy, not smaller energy, just give just the enough energy so that the outermost electron leave the atom and go away, leave the atom, and that electron just go away. Yeah. And then what happens? So let's say, so you have a potassium here, and suppose you give some here. So I have stayed some time. So you give some energy. This is the potassium, it is a gaseous state, right? And then there is a one electron outermost orbit of that potassium. Give enough energy. So let's say that I is the energy here. Yeah. So give that much energy to this gaseous potassium atom, and that one of the electrons from the outermost orbit just fly away. So this leave this guy, the potassium. That electron is no more with the potassium. Why? Because you give too much energy to the potassium, and then just that one of the electron is knocked out. Yeah, it's a very important concept. Just like what you did this time in the 106 lab, something like that. So they call this spectroscopy. Yeah. So this one, and then what is left here? So potassium was neutral, but it's one of the electrons, the negative charge left. So now potassium becomes the plus charge, right? Because one of its electron, at the beginning it was neutral, one of the electrons just fly away, the negative charge fly away. Now it becomes, so this is called the ionization. So this is called I1. So how much energy we should give here is that 490 kilojoule per mole. Meaning that if you take 6.023 10 to the power 23 potassium atom, and if you want to ionize that like this, you need to give this much heat energy or the electrical voltage or something like that. Yeah. Either you can heat or you can give the electrical potential. So in the laboratory, we don't heat that much. We just use the electrical potential. So from outside, we just give the electricity here, so that one of the electrons just kicked out from that atom and it becomes the plus. So that is called the ionization energy. So how much energy we need here to kick out one of the electrons from the valence shell of the potassium? 419, right? Now, this is called the first ionization energy. But if you want to kick out another electron from this guy, now you have the P plus here, this guy, right? Now, because this already has a potassium has many electrons, you already kick out one and you come here. Now, if you want to kick out another electron from here and want to make Pa2 plus, you need to give too much energy here, and that amount of energy is 3051 kilojoule per mole. Very rarely people, you never look any chemistry book, you will not see K2 plus, because the too much energy, 3051 kilojoule per mole of energy need to give to this one, so that the another electron can be knocked out. So that's almost impossible. Yeah, unless you are doing the very high energetic reaction. In normal situation, you can have something like this. Make sense? It's too much energy you need to supply. All right. Yes. No, anything. There are many things we will talk about more. There is also periodic trend, anomalies, and we talk about this. Yeah. So to kick out one electron, we call the amount of energy we call the first ionization energy. If you want to kick another electron from that one, we need to call that ionization energy, and that's 2V. Yeah. Good. Hopefully you understood something. All right. Thank you everyone there. How do we do it? And then